Well, as the song says, doing old exams, doing old exams, getting lots of practice, doing old exams. So our goal is practice. The more we practice, the better we get. And we look at old exams because there's a tendency not necessarily to have the same problems, but to have similar problems. As they say, math may not repeat itself, but it often rhymes. So here we go. We're going to be taking a look here at the Math 165, that's Calculus 1, Exam 1 from Fall 2022. We've got 7 problems, so that'll be a lot of fun. And of course, because we want credit, we'll put our name and we'll call ourselves Answers. That's a great name. Well, let's get going. So the first problem. Find the points x, y on the graph y equals x cubed plus 3x squared minus 4x, where the tangent line has slope 5. Now there's a couple of key points, but of course I think the first one I'd look at is to say, oh, there's tangent line and slope. And that means something. So when we see something saying, oh, I want to know something about the slope of the tangent line, what it's really saying is I want to know something about y prime. And what do we want to know? Well, we want the slope of the tangent line to be 5. So y prime should be 5. Okay, so that's what we're after. We're after all the points where the derivative is equal to 5. So we say, okay, great. Do we know the function? Well, yeah, they gave us the function. This is our curve. So we find the derivative of y prime. Well, the derivative of x cubed, 3x squared, derivative of 3x squared, 6x, and the derivative of minus 4x is minus 4. And we set that equal to 5. And now we should solve. So let's bring the 5 over. I mean, this is a common strategy, is to set something equal to 0, because 0 is a magical number. So we subtract 5, minus 4 minus 5 is minus 9. And I say, oh, they all have factors of 3. We go ahead and divide out by 3. X squared plus 2x minus 3 equals 0. And now, if they love us, our math teachers, that is, if our math teachers love us, this will factor nicely. Now, here's the thing. They do. They do love us, and they want us to succeed. And so we should anticipate that things will factor nicely. And indeed, if they didn't factor nicely, we might be a little suspicious. So here, well, what happens? Well, if it were to factor, it would be x something. And, well, we need two things that multiply together to give us negative 3. Well, okay, it's 3 and 1. That's when we can do 3. And, well, they need to add together to give 2. And multiply, minus means they have different signs. So I think that plus and 3 and minus 1 should work. Now, of course, you can try different variations. We'll double check. We get x squared minus x plus 3x is 2x and minus 3. So, okay, phew, works. Set that equal to 0. Now, this is why we like 0. If things multiply and we get 0, something had to be 0. So, from that, we get x equals negative 3. And that's when x plus 3 equals 0. And x equals 1. That's when x minus 1 equals 0. And now, are we done? Well, no. Okay, so we have to be careful, right? We certainly have done things. We've made great progress. But what we've done is we figured out when does y prime equal 5. So we know for which values of x, y prime equals 5. But the question says find the points x comma y. All right, so we've got the first half of the points, the x values. So we need to find the second half. We need to find the y. Well, all right, well, that's not too bad. So let's, we plug each one of these into the y equals, not the y prime, because if we plug into y prime, we're going to get 5. And that's not what we're after the y. So we plug it into the y equals. So if we start with x equals 1, might as well start with the easier one first. you know, get the victories when you can. What do we get? We get y equals 1 cubed plus 3 times 1 squared minus 4 times 1. 1 plus 3 minus 4 is 0. Done. Okay, that was good. Well, let's do the other one. X equals negative 3. Okay, so we get y equals, and here we'll have negative 3 cubed plus 3 times negative 3 squared minus 4 times negative 3. Well, that's minus 27, because when you cube a negative, it's negative. Here you get 3 times 9, which is plus 27. Aha, cancel, cancel. Minus 4 times minus 3 is 12. So we get 12. Now what we do is we have our x, y, our x, y. So it turns out there's 2 points, 1, 0, and negative 3, 12. And that's it. We found the points x, y, which are on this graph where the tangent line has slope 5. All right, nothing too bad. So we move on to the next part, part B. Find the equations of the tangent lines at the points found in part A. Now, the good news is, if I'm looking for a line, it doesn't matter, tangent line, any line, I need 2 pieces of information. It's always the same. The things I need a point and I need a slope. Now for us, we know our slope is 5, because that's where we always start. So we're always going to have our slope equal to 5. So the only thing that we have to do is say, well, what are the points? Well, they're these points here. So if we start with 1, 0, what do we have? Well, let's just remind ourselves of how to do a line. So oftentimes it's written in the form 1 minus y naught is equal to m x minus x naught. This is point slope formula. And for our m, that's our derivative. So I'll write that, let's say f prime of a. Our x value oftentimes is a, and our y value is the value on the curve. That's f of a. So this can also be written as y equals f of a plus f prime of a times x minus a. Our x, y on the curve, our slope. So for us, if we start with 1, 0, we get y equals 0, the y value, plus the slope, 5, times x minus the x value, 1. Or that's y equals 5x minus 5. Okay, so that's one of our tangent lines. If we go with our other point, y equals our y value, 12, plus our slope 5, x minus our x value, minus 3 becomes plus 3. Okay, so, well, what do we get? Y equals 5x. Well, yeah, so I always going to have slope 5. Then we have 12 and 15 makes 27. And we're done. That's it. That's the problem. Great. Fun problem. And, you know, it's kind of expected, especially on the first exam, we should see problems involving tangent lines. It's one of our big topics. And so we want to make sure we know how to find tangent lines and piece things together. And of course, make sure we follow instructions. So if we had given our answer as 1, negative 3, we would have lost a few points. And our goal is to get all the points. You know, got to get them all. All right, well, one problem down, a few more to go. For our second problem, we have that the position of a particle as it glides along a horizontal track at time t seconds is given by the function s of t. So the reason they chose s is in physics they often represent position with the letter s. So s of t is t squared plus 21 over t plus 2 feet from a point of reference. And we're going to have t is greater than or equal to 0. Find the times t such that the particle is at rest. Include units with your answer. Now, okay, we actually can do the second part just to note is units. Well, we're looking for time. Time is in seconds. Okay, good. So since we're looking for a time and we want units, our answer is something seconds. So we'll remember to put the seconds on there. What's the key phrase here? Well, the key phrase is at rest. What does it mean for something to be at rest? Well, it means there's no motion. It's moving, and it's sort of like, let me break. And then it moves again. It might move in the same direction or reverse direction. So you say, okay, so movement is 0. How do we go from position to movement? Well, movement is our change in position, so it's about the derivative. So here we say, okay, if I want to understand how things are moving, I look at s prime of t. To be at rest, I set it equal to 0. So the question is asking us, find the derivative, set it equal to 0. And now that we know that that's the question, it makes it a little bit easier to figure out how to start the problem. We say, oh, well, let's start by taking our derivative, and once we have that, we'll set it equal to 0. Life is good. Bob's your uncle, and that's great. All right, so let's start. We'll start here. S of t is equal to t squared plus 21 over t plus 2. And we say, okay, what do we have? Well, we have a ratio, or you might call it a quotient. One function, quotient over another. I don't know how you would say that, but this is a quotient rule. I say, okay, all right, so if I'm looking for the derivative, what goes on? Well, we're going to take the bottom, just t plus 2, times the derivative of the top, which is 2t, minus the top, t squared plus 21, times the derivative of the bottom, 1, all of that divided by the bottom term squared. Well, let's clean it up a little bit. Now, why are we cleaning it up? There's 2 reasons we're going to clean this up. One, we want to set it equal to 0, so we'd like to just have that simplified. But there's a little extra thing that's going to happen. Maybe we glanced, and you notice how it says find the acceleration? And we said, oh, the second problem, that's after acceleration. That's the second derivative, which means you've got to take the derivative of the first derivative. And there's a good rule of thumb that says, if I'm going to do something with this, I better simplify at some point. All right, so we're going to simplify so that things become, well, as the saying goes, simpler. Okay, so what do we have? Well, this is 2t squared plus 4t, great, minus t squared, and subtract 21, because the minus sign goes to both terms. And divide that by t plus 2 quantity squared. Okay, so this equals 2t squared minus t squared is t squared, then a plus 4t, and a minus 21 over t plus 2 squared. And that's about as simple as you can get. All right, now, what comes next? Well, we set the derivative equal to 0. Well, how can I have a quotient equal to 0? And the answer is there's just one thing that can happen, which is the upstairs part, that t squared plus 4t minus 21, that part has to be 0. So we say, okay, so s prime of t equals 0. That says t squared plus 4t minus 21 has to equal 0. And another quadratic. Will this one factor? I hope. Well, we should expect. Again, if it didn't, we've always got the quadratic formula. So even if it didn't, that's okay. Nothing to worry about. No stress. It's just calculus. Nothing to worry about. All right, so what do we have? Well, what do we want? Let's suppose it were to factor. I'm pretty optimistic about these things. So, okay, so there's a t and a t. Well, we need to multiply together to give 21, and negative 21, and add to give 4. Well, okay, how do I multiply to get 21? I can do 1 and 21. Hard to get 4 out of that. 7 and 3. Oh, I can get 4 out of that, because if I take a plus 7 and a minus 3. So I think that might be it. Plus 7 and a minus 3. We double check. T squared. Good. Minus 3t plus 7t. Great. And a minus 21. Perfect. Nailed it. Now, what does this tell us? It tells us that t is 3 or negative 7. Okay, wow. Well, it did say there were times t, right? So maybe there are 2 answers. But wait a second. We are careful. And there's something that caught our eye. T has to be greater than or equal to 0. So what does that do? It says it can't be negative 7. That's out. Not that. Okay, so that leaves us with just one choice. It must have been the case that this happened at time t equals 3 seconds. That's the only option. And that's the answer for part A. Okay, good. One part down. Let's go into the second part of this problem. It says for each t, well, there's only one, so we just have one t found in A. Find the acceleration of the particle and include units with your answer. Now, for units, we can do our units pretty quickly, right? Because our position is feet. And so it's going to be feet, and then it's going to be second squared, right? Because each time you take a derivative, you're really building up your denominator. So the first derivative, feet per second, that's your velocity. Then your derivative velocity acceleration, feet per second per second. Well, that becomes feet per second squared in terms of your units, although that sounds weird when you say, well, what is a square second? Well, it really means that there's an iteration, feet per second per second. Okay, so what do we do? Well, acceleration, second derivative of velocity. And so in particular, our goal is to find, oops, I can spell the word goal, is to find s double prime of 3. All right, so here we go. We thankfully simplified our s prime. Good for us. So we can say, all right, s double prime of t, well, it's again a quotient rule. So we say, all right, we're going to take the bottom, t plus 2 squared, times the derivative of the top, 2t plus 4, minus the top, t squared plus 4t minus 21, times the derivative of the bottom, which is 2, times t plus 2 to the 1 times 1. If we just do the chain rule, all of that over the bottom squared. So t plus 2 squared squared is t plus 2 to the 4th. Okay, now this one you're probably like oh, do we have to simplify that? And our answer is no, we don't. Because what do we need to do? We need to find s double prime of 3. So let's just plug in 3. There's nothing that requires us to simplify because we're not trying to solve anything with it. We're not going to take a future derivative, so plug it in. So we have s double prime of 3 is equal to, okay, so everywhere I see a t, I put a 3. So we have a 3 plus 2 squared. Okay, so I'll write that as 5 squared. Then I have a 3 times 2, which is 6, plus 4 is a 10. So 10. Subtract. Now, 3 squared is 9. 4 times 3 is 12. 9 plus 12 is 21. Subtract 21 is 0. In fact, we anticipated a 0 because this was what we had set equal to 0 when we were solving for part A, right? So when we plug in 3, of course we should get 0. So we're going to get 0 times 2 times 5. Well, we don't really care. Once it's 0, it's 0. And then downstairs, well, we have 3 plus 2 is 5 to the 4th. Well, we can cancel off. In fact, really, if you think about 10, that's 5 times 2. Of course, all this goes away. So we have 3 5s upstairs, 4 5s downstairs. And so we're left with a single 2 upstairs, a single 5 downstairs, and we toss in our units because, well, it told us to, and we want the credit because, that's our goal, get all the points. And that's our answer. 2/5 feet per second squared. And we're done. Done with number 2. A good problem. They like application problems, and usually our application problems are very simple. But don't worry, the more calculus you do, the more interesting your applications will become. So, let's enjoy it while we have it for now. Okay, the third problem. Use the limit definition of the derivative to compute the derivative f prime of x for the function below. F of x is the square root of 5x minus 2, and of course it says assume x is greater than 2/5. The only reason that this is included, in case you're wondering, wait, why did they specify it, is because then the function is well defined in terms of just the real numbers, the numbers we're used to. There's nothing special about what's going to happen that requires x to be greater than 2/5. And, well, they're very explicit here. Look, they made it very bold. They say, you must use the limit definition, and solutions using other methods will not receive credit. Now, there's a few things that are a guarantee in life, but one of the guarantees that you'll have is on the first exam in Calc 1. You will have a problem that states, use the limit definition to find a derivative. Because this is getting into the machinery. How do things work? And they care a lot about these problems. So anticipate. Now that we know it's coming, we're going to make sure that we're in good shape. And so how do these problems go? They're always going to go the same way. First off, we should know the limit definition. And there's 2, but there's one that we always like. So the one I recommend you use is to say, well, look, f prime of x, the definition, is the limit as h goes to 0 of f of x plus h minus f of x over h. If all you did was write this down, you would get a couple of points. And so at the very least, you're like, I'm grabbing my couple of points and I'm going to get this. Now, a couple of comments here, because I've seen these exams before. I know what they're looking for when they're grading. Make sure you always are consistent with putting that limit there, and you don't take the limit away until you're at the end. You'll see when we get there, because they check for that. And if you drop it too early, you'll lose a point. The other thing is to say, well, what's the game here? What is it we're trying to achieve? And it's always the same big idea. The big idea is to say, if you were to plug in h equals 0, you get a 0 over 0. So you want to somehow get rid of 0 over 0. So the idea is we're going to do some manipulation on the upstairs part that pulls an h out so we can get cancellation. So in other words, we're looking to cancel some h's. That's the game. That's the whole game. Now, how do we do that? There's basically only 3 kind of algebra tools that are going to show up. So you're going to have things like multiply by conjugates, and this will certainly show up if, for instance, you have the following, namely if you have a square root. So if you see a square root, you're going to see multiply by conjugates. We see a square root, we know there's multiply by conjugates coming up. There's going to be adding fractions, and if anything shows up downstairs, that would be there, but we don't, but that's okay. We're just reminding ourselves. And then, of course, there's factoring and expanding. And that's it. That's the game. you basically, everything is going to come down to one of these three things. So if you're comfortable with those three algebra tools, you'll be able to answer these questions. Okay, let's go back to our problem now that we've rambled. Well, you know calculus teachers, they love to go off on tangents, and so that's the danger of watching these explanations. Okay, so what happens? Well, now we come to, after the definition, one of the hardest parts is making sure to know what goes on. So notice this says plug in x plus h. So what do you do? And the answer is really not too bad. It's to do the following. It says everywhere where I see an x in my expression for my function, I put x plus h. That's it. So it's not there's a plus h on the very end. No. That's not what happens. It's everywhere where I see an x, I put a plus h. So this would be a square root 5, and instead of x, I put parentheses x plus h and a minus 2, and minus the square root 5x minus 2, and downstairs h. Okay, now comes our algebra. And say, all right, what do we need to do? Well, first off, let's clean things up. So we're going to do some expanding on the inside. Basically, we're going to take care of that plus h and just expand it out. So we can write this as the limit as h goes to 0. And we'll have square root. We'll have it as 5x minus 2 plus 5h. And then minus the square root 5x minus 2 all over h. Okay. Now we say, this h inside the square root, somehow we got to get it outside the square root because we need to get that to cancel with the h downstairs. So we say, well, what can we do to get things outside of square roots? And we're like, it's right there at the top. Multiply by a conjugate. So the way you do that is you multiply by the same expression, except instead of putting the minus, put a plus. Okay, and if you multiply top and bottom, then you're okay. If you only multiply the top, well, that changes what you're trying to take the limit of. But if you multiply top and bottom, it's like multiplying by 1. And multiplying by 1 is good because it doesn't change anything if you multiply by 1. But of course, it's not just anyone, it's the chosen one, a well-chosen one. Now, comment. We are going to multiply things out upstairs. We're not going to do it downstairs. The reason we multiply out upstairs is multiplying things out upstairs is going to simplify things. And that's the whole point of multiplying by the conjugate. Downstairs, it doesn't simplify. So we only carry it out on the parts where it actually helps us. Where it doesn't help us, we don't do it. Be smart. Don't start. Okay. Well, start the problem. It's just, my point is, when you're thinking about, where do I do operations, where do I not do operations, do things where it helps simplify. Don't do things where it complicates. Sounds simple, right? It sounds like philosophy for life there. But, all right, so what happens? Well, a minus b, a plus b, you get a squared. That gets rid of the square root. 5x minus 2 plus 5h. Then minus b squared. So subtract 5x minus 2. All of that is over h. And remember, we're not going to multiply it out. So we get 5x minus 2 plus 5h plus square root 5x minus 2. All right. Now, we've done some good things. We've gotten the h outside of the square root. And so you say, does anything simplify? We should anticipate the answer is yes. The 5x's cancel. The minus 2's cancel because of this minus. And so the numerator is actually 5h. We'll go ahead and write that down because we've got plenty of space left. And so we have a limit. H goes to 0. 5h over the whole thing downstairs. Okay, no problem. And, okay. And then we say, aha, the h's cancel. And that, remember, was our whole game from the start. Do some manipulation until we can get h's to cancel. And now that the h's cancel, we've effectively have removed the 0 over 0. In other words, we solved the problem that was stopping us from making progress before. Nice! That's great news. Okay, so now we'll take the limit. Remember, we've been writing this limit down because we're like, we don't want to lose any points. And until we've actually taken the limit, we've got to keep writing it. But now we take the limit because we solved our 0 over 0. So equals upstairs 5. Downstairs, right? Because anything where there's an h left, there's only a single h left here, those h's are gone, that becomes a 0. So you get a square root 5x minus 2, then that 0, plus a square root 5x minus 2, which we can really write that as 5, divide by 2, square root 5x minus 2. And we're done. That's it. There's our answer. Now, that's doing it using the definition. Now, notice carefully here. It says you must use the limit definition, which is what we did. Solutions using other methods will not receive credit. So, but it doesn't say we're not allowed to look at other methods. It just says it can't be part of a solution. So what we can do is something very simple. We can do a quick check. So here's our check. Say, well, look, if I'm taking the derivative of, and we'll write this as 5x minus 2 to the 1/2, well, it'd be 1/2 5x minus 2 to the negative 1/2, right? Because you bring the half down using the chain rule, subtract 1, and then times that by 5, which is the same as 5 over, and then 5 upstairs, the 2 goes downstairs. This minus half means it's a square root downstairs. And we say, yep, that matches. So now we see that doing it the more direct method, in other words, using the rules that we invested our time in learning, we got the same answer. So this helps us know that, yeah, this is probably, we did something right. Now, if these did not match, we would double check our work. We'd probably double check here first because it's shorter. And then we say, okay, what did we miss? What did we miss? Because as the great philosophers have said, we should check ourselves before we wreck ourselves. All right. Well, anyways, 3, done. We know it's coming. We're going to be ready. No surprises. Good. Done, done, done. So number 4, let f of x equals ax squared plus b square root of x. Find ab such that the following two statements are true. The average rate of change of f of x from 0 to 4 is 1. Okay? The instantaneous rate of change of f of x at x equals 1 is 2. So this is a problem which involves average rate of change and instantaneous rate of change. And of course they say, oh, there's a and b, 2 things to find, and they gave us 2 pieces of information. So that sounds like a good deal. All right, so let's remind ourselves about a few things. Okay, so average rate of change. We'll start there. What that does is it says, okay, compare, what's the value at 0, what's the value at 4, and versus how long it took to go from 0 to 4. In particular, for us, we would say, well, we want f of 4 minus f of 0 over 4 minus 0. So that's the average rate of change from 0 to 4. The change in y over the change in x. Okay, maybe that's a simple way to remember it. Change in y, change in x. How does the function change? Take the difference. How does the input change? Take the difference. Now for us, well, the good news is when you plug in 0, a times 0, b square root of 0, 0. So actually, wow, those are both 0 in our case. So we end up with, well, f of 4 is 16a, and then square root of 4 is, well, 2b. And of course, you know, that raises the great philosophical question, to be or not to be? Well, it is to be. So that's 4a plus 1/2 b. So in other words, currently, if we just say it's a and b, where a and b are some unknown constants, and you say, well, what's the average rate of change from 0 to 4? It's 4a plus 1/2 b, and, well, that equals 1. Okay. Instantaneous rate of change, let's do that. We'll switch colors here. Instantaneous rate of change has another name, aka derivative. So we want the instantaneous rate of change at 1 is 2, so we want f prime of 1 to equal 2. Okay, so let's talk about f prime. In general, we have that f prime of x is the derivative of x squared. It's 2x, so it'd be 2ax. And then square root of x, okay, remember square root of x is just another way to write x to the 1/2. X to 1/2 is a more calculus-friendly way to work with things, because that's how our rules are phrased. So square root of x, the root of that, would be the 1/2 comes down, so 1/2 b, and then it's x to the minus 1/2. So f prime of 1 is 2a times 1, and 1 to the minus 1/2 is also 1, so 1/2 b, and then we're told that should equal 2. All right, so we took our two statements, and we got two equations, and we're into a classic calculus thing. Two equations, two unknowns. You're going to see that so many times over this semester and subsequent semesters. We're going to just get really good at this. All right, so let's write them down on top of each other. 4a plus 1/2 b equals 1. And then 2a plus 1/2 b equals 2. And, well, it's two equations, two unknowns. There's lots of ways to approach it. The basic mantra is to say two equations, two unknowns would be simpler if it were one equation, one unknown. So, oh, okay, great, let's do that. And how do we do that? Well, we can get it down by either eliminating a variable, and that's done by substitution or elimination. So I like to eliminate by combining things in smart ways. So for instance, I'm just going to take these two equations. I see that they both have a 1/2 b involved, and I'm going to subtract. 4a subtract 2a is 2a. 1/2 b subtract 1/2 b is 0. And 1 subtract 2 is -1. So that says, oh, a should equal minus 1/2. Now that we know that a equals minus 1/2, well, we can come back into really either equation. Let's suppose we start with the first equation. 4 times minus 1/2 would be minus 2 plus 1/2 b equals 1. Or 1/2 b is equal to 3. So what does that tell us? Well, it tells us that b should be, multiplied by 2. B should equal 6. And so there's our answers for A and B, because our problem said find A and B. So our two conditions gave us two relationships. We got two equations, two unknowns. We solved our two equations, two unknowns, and life was good. That was actually pretty fast, right? Follow the directions and it works out. Wonderful, wonderful. Right. Time for the fifth problem. Compute the following derivatives. You do not need to simplify. So we're after computing derivatives, which means we're really being tested here on our rules. Do we know our rules for differentiation? 100% do not do the limit definition. So when we talk about rules, we're talking about things like product rule and chain rule, occasionally a quotient rule. It looks like there's no quotient here, so that's good news for us. And then the rules of the various functions involved. So you got to think about, okay, what rules are being tested as you go through. So let's look at the first one, part A, the derivative of 1 plus e to the 3x times tangent of x. Now, when I'm looking at this problem, I see that really I have two parts, and they're being multiplied together. So there's the 1 plus e to the 3x multiplied by the tangent of x. That's signaling product rule. So you say, all right, cool. So product rule says, what do? Take the derivative of the first, so the derivative of 1 plus e to the 3x, and then we say, okay, well, the derivative of 1 is 0, derivative of e to the 3x. Derivative of e to the 3x is actually even a chain rule inside, right? What is derivative of e to the 3x? It's e to the 3x times the derivative of the inside. There's just layers and layers. So these rules, or I should say these problems are like onions. There's layers involved. And they're also like onions in that we may shed a couple of tears along the way. But okay, so getting back here, the derivative of 1 plus e to the 3x is 3e to the 3x. All right, derivative of the first times the second. Leave that alone. Leave it alone. Because, the way I like to think of the product rule is everybody gets their turn, right? So in this case, the first function got to have its turn as taking derivative. Now add to that, now it's the second piece that gets its turn. What's the derivative of tangent? It's secant squared. All right, derivative of the first times the second plus the first times the derivative of the second. And what happens next? Well, what happens is we say, hey, they told us we don't need to simplify. Now, that's actually in the rules on the front of the exam. So when they go and really specify you don't need to simplify, then we're really going to not simplify and say, hey, we found our derivative, and so we'll be happy with that. Life is good. Done. Well, that was not so bad. What about the second part? Because, well, there's a part B here. The derivative of the cubed root of sine of x. Now, it's cubed root. That's what that little tiny 3 is indicating. So first thing is, I would want to rewrite that in a calculus-friendly way. Calculus-friendly says, oh, make it so it's an exponent. So this is sine of x to the 1/3 power. When I'm looking at this, what do I see? Well, I see a function, sine of x, inside a bigger function. So it's layered, right? Function in function. It's different than, if we come back here, part A, see how they weren't inside each other, they were next to each other. Next to each other, product rule. Inside each other, chain rule. Chain rule. Yes, it's the best rule. All right, so how does the chain rule work? Well, it says, start with the derivative of the outside function. In this case, it's the power to the 1/3. The 1/3 comes down. Leave the inside part. That's the sine x. That part, leave it alone. Leave it alone right now. You're going to come back to it. Now, of course, when we take the power comes down, we subtract 1. That's minus 2/3. Okay, are we done? No. Now is when we take care of the inside. Say, okay, times by the derivative of the inside. And the derivative of sine, is it cosine or negative cosine? It's cosine, right? We know that. Sometimes in the heat of the moment, when you're in the middle of a calculus exam, it feels like, wait, which is it? Oh no. And you panic. But no, we're not going to panic. We're just going to write it down. And then we say, hey, that's great. We'll just leave our answer like that, and we're good. You see, they don't have to be long problems. It's just testing our basics, right? And just think about, how do things fit together? Are they multiplying? Are they inside one another? Or do you have some sort of division going on? And once you figure out how all your pieces connect, you know which rules to use. And of course, once you know the rules, then you just go. You just do it. And of course, it's easy to say, well, you just do it. But that's how a lot of calculus works. Once you know the rules, it flows. All right. Now we're up for number 6. So look at the function f of x, which is 3x minus x squared, divided by x squared minus 9. And it says part A, find all horizontal asymptotes of y equals f of x, or explain why there are none, and justify your answer with appropriate limit computations. And then there's part B, which says find all vertical asymptotes of y equals f of x, or explain why there are none. Justify your answer with appropriate limit computations. All right, so let's start, right? Now, horizontal asymptotes. What does that mean? Well, horizontal is when we're going, side to side. Now, when we're talking about horizontal asymptotes, that's saying, well, we want the x going to plus or minus infinity. That's what we're after. Okay, so let's take a look. We're going to take a limit as x goes to infinity of our function, which is 3x minus x squared over x squared minus 9. Okay, that's great. And we know we're going to take limits because it tells us to justify it with limit computation. So we have to put a limit computation in there. Now, what can we do? Well, when we have polynomial or polynomial and we're going to infinity, the key is, what's the dominant term? It's the x squared. It's going to dominate all these other terms. So we're going to say, okay, the x squared is the dominant term. So what we can do is we can actually multiply top and bottom by 1 over x squared. Now, sometimes it gets a little bit subtle when you have things like square roots or absolute values, but that's not here, so that's for a different day. Why worry about subtlety? So we have a limit as x goes to infinity. Now, why did I multiply by 1 over x squared? Well, I said that the growth, the biggest thing, behaves like x squared. So essentially what we're doing is we're putting the brakes on and say, slow down, whoa, take it easy, don't get too excited. So that's what's happening by multiplying by the 1 over x squared. We're pulling the growth down so that instead of things blowing up, they level off. That's what's going on. So we'll get a 3 over x minus 1. Then downstairs we'd have a 1 minus 9 over x squared. And now we say, okay, as x goes to infinity, well, anything with an x downstairs goes to 0. So we get a minus 1 over 1. All of these other terms go to 0, which is negative 1. Well, we should check both sides, plus and minus. Now, this is going to feel very nothing changed. Well, because actually with polynomials, nothing does change. Like I said, if you had square roots involved or absolute values, yeah, subtleties, be careful. The right amount of, I don't know if it's going to involve square roots, but just square roots can throw you off a little bit. And absolute values can throw you off a lot. Because you have to say, well, wait, what's the sign? What's going on, plus or minus? And so think about that if you have one of those two situations. But really, the only thing that's happening is there's a minus sign. Everything else carries through the same way. And we see that, lo and behold, we get minus 1 and minus 1. So we get that y equals minus 1 is only horizontal asymptote. And then we say, great, life is good. That's our answer. Okay, well, that's part A, the horizontal. But there used to be a TV show that says, we control both the horizontal and the vertical. And, well, it was about the outer limits, right? How appropriate for this type of a problem. So, part B, find the vertical asymptotes of y equals f of x, or explain why there are none. Okay, so let's think about vertical asymptote. Now, when we're talking about vertical asymptote here, well, what that's really saying is that the y value is blowing up. That's what we mean by the vertical asymptotes. The y is going big. So as a reminder, it's 3x minus x squared over x squared minus 9. Okay, so when we're looking for things to blow up, well, there's a couple of things that can do it. If you have like a tangent or secant or something like that, okay, that causes a blow up. But really the key is to say you have a division by 0. So you're looking for 0 downstairs in our denominator. Okay, so potentially we say, okay, we might have asymptotes when x squared minus 9 equals 0, or when x equals plus or minus 3. All right, so those might be asymptotes. Maybe. Well, how do we check? Well, we have to do a limit computation. So let's check at, which one should we do first? Let's check at plus 3. Why not? So x approaches 3. What do we have? Well, we have 3x minus x squared over x squared minus 9. And what you do is you plug it in, right? You should always, anytime you see a limit, you should just say, plug it in, see what happens. And if you get a good answer, you're done. And if you don't, you start going, 9 minus 9, 0. 9 minus 9 is 0. So right now, this is going to 0 over 0, which means more work. More work. Doesn't mean an asymptote. Okay, so we say, okay, well, wait, that says you should get some cancellation. And now our great aha, this, notice upstairs we can pull out, I'm going to pull out a negative x. So it becomes negative x, and then it becomes x minus 3. And downstairs, that's x squared minus 3 squared. That's x minus 3, x plus 3. We really expect, since we plugged in 3 and we got 0 both upstairs and downstairs, they both should have a factor of x minus 3 involved. And we say, okay, well, the x minus 3's cancel. And now we say, so this is a limit as x approaches 3 of minus x over x plus 3, and plug in 3. And what do we get? We get negative 3 over 6, which is a reasonable number. It's, we don't really care, what the value is. It's negative a half, but it converges. So what does this mean? It says, well, x equals 3 is not a vertical asymptote because it converged. Okay, so that's good. Now, what about negative 3? Okay, yeah, we still have to check that one too. Okay, so the limit as x goes to negative 3, okay, we got 3x minus x squared over x squared minus 9. So that'd be minus 9, that's minus 18 over 0. And this, sorry, I should put an arrow here, not an equals. And that means vertical asymptote. If you have a number over 0, it's a vertical asymptote. So there is a vertical asymptote at x equals negative 3. Now, we don't have to be more precise. We don't have to say, it's going to infinity or it's going to minus infinity. It turns out in this case, it's one of these things which goes, I don't know which one, but it's one of those two, where on one side it goes to positive infinity, one side it goes to negative infinity. We're just asking, where is it? And when you see a non-zero number over 0, that's saying, hey, I have something not close to 0 divided by something close to 0. And when you divide by something close to 0, you get huge. You blow up. And that's what causes vertical asymptotes. So we say, lo and behold, x equals negative 3 is a vertical asymptote. And that's it. That's the only one. And there we go. That's our answer. Now, you might ask yourself a question here. You might say, hey, I see I get these x minus 3's to cancel. So, is it the case that f of x is this? Does f of x also equal question mark? Well, what would it be? Negative x over x plus 3? What do you think? Is this another way to write f of x that's valid? Well, kind of, but technically no. And you might say, well, wait, why are these not the same? And the answer is, at 3, you have different values. At 3, this makes perfect sense. At 3, this is undefined. So it's almost the same, except at that one point But even in math, one point is enough to say, well, no. Close, but no. So anyways, that's just a side note. Okay, good. All right. So one vertical asymptote, one horizontal asymptote. Life is good. Life is great. Number 7. For the following questions, use the graph of y equals f of x below. Okay, so this is y equals f of x. That's good for us to know. We'll just put a note here just to remind us. And, it's a little bit disjointed, but that's okay. So, part A. Find and classify as removable, jump, or otherwise the discontinuities of f of x on the interval -4 to 4. Justify your answer with appropriate limit computations. Now, of course, the nice thing is that the appropriate limit computations is just to say, use the picture. We don't have to be anything fancy. All right, so where do we look for discontinuities? Well, we look for where, if we think back to our adage when we were young people, well, you're still young people, but when I was a young person, and don't worry, math hasn't changed that much since I was young. They said, well, okay, where do we look for discontinuities? It's anything that's a surprise. Or you could say, well, you have to lift your pencil. And looking at the picture, we say, well, the only thing that's a place where you really have to lift your pencil to do anything are at those two locations. Everything else, life is good. So we say, okay, so we have two candidates at -1 and at +2. Now, are these removable or are these jumps? Or are they something else? Now, other basically means there's some sort of blowing up going on. So that would be, say, for example, if I had a vertical asymptote, but okay, there's no vertical asymptote involved. Now, removable says I have a hole and I can fill it in. So notice that too, I have a hole that says, oh, I should be here, but I'm there. So we say, aha, x equals 2. We'll say it's removable. Now, why is it removable? What we need is to show, well, the limit as x approaches 2 of the function f of x is equal to 1, but I got ahead of myself, f of 2 is equal to -1. So the fact that the limit exists, but the value of the limit and the value of the function disagree is what makes it removable. All right. Now, what about -1? Well, where do I fill the hole? I can't fill it in here. I can't fill it in there. It's just, I have to really I have to lift up my pencil regardless of what I choose. So x equals -1. That's a jump. Now, how do you find jump and how do you verify it? Well, jump is when you have this going on, right? It's like the two sides disagree. So what you do is you look at one-sided limits. So the limit as x approaches -1 from above, well, okay, as we approach from above, it's going to this place. It's -2. Oh, I forgot to write f of x is -2. The limit as x approaches -1 from below, okay, that's from over here, is +2. And the key is these are not the same. So if your one-sided limits disagree but exist, it's a jump. If the one-sided limits agree, which means the limit exists, but the function disagrees, it's removable. If the limits agree and the function agrees, it's continuous. Other says infinity is involved. Okay. Or the limit just can't even exist. So I should say like sine 1 over x. If you're familiar with sine 1 over x, it's like, okay. And then all of a sudden, it goes crazy near 0. But okay. Other is their limit doesn't exist. We'll just put it that way. Okay. Now, here we go. Find and classify as removable, jump, or other the discontinuities of f of x squared on the interval -4 to 4. Justify your answer with appropriate limit computations. Okay, so what's happening here? Well, we're squaring f of x. Now, we can just put a little mental note. Since f of x will be continuous, well, f of x squared will be continuous wherever f of x is continuous. So only have to look at, so we only have to check answers from part A. So where are the candidates? There's a candidate at 2. Well, at x equals 2, we'll do a quick check. Well, what do? Well, we'll take the limit as x goes to 2 of f of x squared, and what do we get? Well, we're going to get 1 squared, which is 1. And f of 2 squared is negative 1 squared, which is 1. And so you say, oh, cool, that means it's continuous at x equals 2. Okay, so actually we didn't even need to do any justification. It's not a discontinuity. Well, you know, you live and you learn. Now what about x equals minus 1? Okay, so let's try this out. The limit as x approaches minus 1 of f of x squared. Well, okay, let's approach it from above first. I can use this and say it's negative 2 squared. So that would be negative 2 squared, which equals 4. The limit as x approaches minus 1 from below of, whoops, I forgot to write down something. There we go. Ha 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 ha. I may have lost a point. I don't want to lose a point. That's not our goal. Okay, limit as x approaches minus 1 from below of f of x quantity squared is equal to 2 squared, which is also equal to 4, which means, oh, the limits exist. Okay, that's cool. So, but okay, but wait, we're not done. What happens at negative 1? So, f of negative 1 squared, whoops, sorry. Let me put this back up here. F of negative 1 squared, okay, back here, it would be 4 squared, so equals 4 squared, which equals 16. So, what do we have? The limit exists, but the function doesn't match the limit. So, x equals negative 1 is a removable I can spell removable discontinuity. And that's it. So, good. That's our answer. X equals negative 1 is a removable discontinuity, and there's the computation. The limit exists, but the function doesn't match the limit. That one's a little tricky. But that's all right. We don't have to worry. We just follow the definitions. We're looking for discontinuities. Look what's happening with the limits and versus what the function says it should be. All right, well, good practice. And who knows what this test will have? I don't know. But I don't think it'll be too far off. We often use similar ideas on these exams. So I hope you do well, and good luck. Have a good day.